In this lesson, we'll talk about composition of functions and inverse functions. First, when we talk about the composition of two functions, it's basically taking one function and putting it inside of another function. So we can consider this function f of g of x. And so the way that this function works is g of x is the inside function, and f of x is the outside function. Let's take a look at this example to make sense of this. Suppose that your pay is a function of the hours worked. This is the case for really anybody who works per hour. And we're looking at it as the pay of x is equal to 8 times x, where x is the number of hours worked. So that would say that 8 is your pay rate, so you'd be making $8 per hour. And then the taxes on your pay as a function of the amount that you paid would be the taxes of x is 0.2x. Basically, I would interpret that as 20% of your income gets paid in taxes. Let's do the composition of t with p. So if we take t of p of x, remember t is your taxes and p is your pay. So what I'm going to do is start by taking the tax function but replacing p of x with its definition, 8x. Then wherever I see an 8x in this function t of x, I will replace this x with whatever is inside the parentheses. So that means I'm going to take t of x would be 0.2 times, in this case it's 8x, which gives me 1.6x as my answer. So the question is, what does this represent? Well, the x in this case was the x for the p function, which was your number of hours worked. And in the ending, you took hours worked to amount paid to amount of taxes. So this is going to be the amount of taxes based on the hours worked. Again, this represents the amount of taxes as a function of the hours worked. Let's do another example. Let's take two functions and simply find an expression that represents both of these compositions. We're doing f composed with g and g composed with f. And so it's important to pay attention to the order here. The outside function and the inside function is going to make a difference when we do these compositions, where they'll switch to be g is the outside and f is the inside. So when we do f of g of x, I'm going to follow the same steps I did a minute ago. I'll work from the inside out. I'm going to get f of g of x is x minus 3. And so I'm going to take a look at the function f. F of x is x squared. And so x is going to be whatever is inside the parentheses. I'll replace this x with x minus 3. And so I get x minus 3 squared. If I write that out, that would be x squared minus 6x plus 9. That would just be your standard FOIL method, or you can use the special product that I did to do it quickly. The other direction, g of f of x, you would start with the inside, which is x squared this time, and then we would go to the g of x function. G of x is x minus 3. So wherever I see an x, I will replace it with x squared. So therefore, I get x squared minus 3. You'll notice that these two are not the same. And that's true in general. When you compose two functions, very often you will get two different answers. So with this idea of composition, let's talk about inverse functions, and then we'll put the two together. The inverse function is often denoted f, and then you've got this -1 superscript. This has nothing to do with exponents. This actually is read f inverse of x. And this is the function that does just the opposite. It reverses the role of the original function. So let's take a look for a moment at this example. You have a pizza shop that charges $10 for a pizza, and then $2 per topping. So if we were to try to write a function for that, let's just call it f of x. And f of x would be, let's see, the charge is a function of the number of toppings. Remember, we always treat it as y is a function of x, so x is the number of toppings, and consequently I've got $10 for my starting cost, $2 per topping times the number of toppings. So that would be the function here. Now, if I want to think of an inverse function, remember the inverse function is going to take everything and do the reverse. So this is what happens. We start with the toppings x. And then let's just go through the function. The first thing the function would do is multiply x by 2. Multiply by 2. And then for the next step, after you multiply by 2, you would add 10. And after we have done that, we arrive at the cost. I didn't give a variable to the cost. Let's just call it y. Now, if I wanted to do this in reverse, I would start with the cost, which is my y value, and then I would do just the opposite. If I'm wanting to reverse this, now instead of adding 10, I should subtract 10. Continuing to go backwards, I get to multiply by 2, so instead I should divide by 2, and that takes me back to my toppings. So the idea with the inverse function is it will take your cost and recover the number of toppings. So just to give this an actual setup, we'll call this thing f inverse of x, and look what it does. It says take your cost, which I'm going to call x in this case, you're going to subtract 10, and then divide by 2. So I have x minus 10 over 2. Now one thing that you might be thinking is I sort of took x in place of y. We'll talk about that just a little bit more. This is your inverse function, and the x's and y's actually do kind of get switched in the process of doing this. Here's the general steps for finding an inverse function. What I want to note is that if you have y equals f of x, what we've discovered was x equals f inverse of y. And you can actually even look back at what I did a moment ago. If you look back at this, if I were to take this expression and solve for x, maybe calling this thing y, I would subtract 10 and then divide by 2, and look, that's exactly what you have. So it's sort of like I solved for x, but then I called the other one x. Here's the steps that actually work. You start out by calling f of x y, you solve for x, and then you would actually switch your x and y and call this thing y equals f inverse of x. Let's jump into an example. Find the inverse of the function f of x equals 4x cubed minus 2. Here's what we can do. We're going to say y equals 4x cubed minus 2. And then we want to go through the process of changing this thing to x equals. We're going to solve for x. So I'll start by adding 2 to both sides. That gives me y plus 2 is equal to 4x cubed. Next step, I'll divide both sides by 4. That gives me x cubed, I'll rearrange it, is equal to y plus 2 over 4. And then to undo a cube power, you should do a cube root. In doing that, I get x is equal to the cube root of y plus 2 over 4. Now that's not my final answer, but notice I have x equals. The final answer is I should switch the roles of x and y to write f inverse of x is equal to. So imagine if I switched the roles, I would say y equals the cube root of x plus 2 over 4. So I'm just going to call that f inverse of x, and the y will become x. So f inverse of x is the cube root of x plus 2 over 4. And that is my inverse. Again, this -1 notation has nothing to do with exponents, except for it's actually used in terms of inverse multiplication. But our general setup is that means inverse rather than anything to do with 1 over or anything like that. Next example. Now this example is going to be a little bit different. Let's start off with y equals 4x over x plus 3. What's a little bit different about this one is I've got a denominator and I have two x's floating around, but I'll show you how to tackle that. The first step I'm going to do is multiply both sides by whatever is in the denominator, in this case the x plus 3. And now when I rewrite this, let's go ahead and distribute this y. I get xy plus 3y is equal to 4x. Now remember, my goal is to solve for x. So what I'm going to do is get everything involving x on one side and getting everything involving y on the other side. So with that said, I'm going to subtract xy from both sides because that term has an x in it. And if I move that, that will get all of my x's on one side and my terms without x's on the other side. Let's rearrange this as I go and write this as 4x minus xy is equal to 3y. Now here, remember I'm trying to solve for x. You might think we're sort of stuck, but the technique at this point is I'm actually going to factor out this x. When I factor out the x, I get 4 minus y and 3y, and look, it does appear like I'm very close to getting x by itself. What I need to do to finish it is divide both sides by 4 minus y. From that, I get x is equal to 3y over 4 minus y. So remember, the final step is you'll switch the roles of x and y to write f inverse of x. So wherever I see a x, it's becoming a y. I'm just calling that f inverse of x. And y will become x. Whenever I do that, I get 3x over 4 minus x, and that is my inverse this time. Now let's consider how the function composition and the inverse functions relate to each other. It actually turns out that the inverse functions have a property that if you compose two functions that are inverses of each other, say g of f of x, if these two are inverses, they will just simply give you x. And if you do f of g of x, it will also just give you x. So what this basically is saying is that if you compose a function and its inverse, they will undo each other and just give you your original input. That kind of makes sense. If you take an x and put it into a function so that it comes down to some y, but then you take the inverse function that would take that y right back to the x, then that's what you're going to get, x. Let's do this example. We're going to compose f and g of x and just show that these two are inverses of each other. So if we were to do f of g of x, remember the rule is start with the inside. G of x is x plus 4 over 3. And then whatever you see in the f function, wherever there's an x, you will replace it with this whole expression. So I get 3 instead of x, I get this whole thing, x plus 4 over 3. And then 3x minus 4 is what I get. You'll notice the 3's cancel, which gives me x plus 4 minus 4. And then the 4's cancel, which gives me x. Let's do the other direction. G of f of x. Again, start on the inside. That's g of 3x minus 4. So now I'll go to g, and wherever I see an x, I will replace it with 3x minus 4. That gives me 3x minus 4 plus 4 all over 3. And now let's start simplifying. The 4's cancel, which gives me 3x over 3. The 3's cancel, and again, I just have x. Because I got x in both directions, that says that yes, indeed, these two are inverses of each other. Now the final question to answer is, when does a function have an inverse? Everything that we have dealt with so far, we said, yeah, we'll just calculate the inverse, and it turned out to work. However, it's not true that every function has an inverse, and so the property that we have that allows this is called the one-to-one property. If you recall, what we defined a function to be was for each input, you get exactly one output associated with that input. However, now we're looking at it a little bit differently, that in addition to every input is only associated with one output, every output is only associated with the same input, which means that if you have two different inputs, those two different inputs must have two different outputs, which you have written here. If x1 does not equal x2, then the function value at x1 will not equal the function value at x2. And it's easy to spot. If you have this property, then you will never have a horizontal line touch two places. If you do, that would be two different x values that have the same function value. So if you have a horizontal line that never intersects the graph more than once, we call it one-to-one, and it also means that it's invertible. So a function only has an inverse when it's one-to-one, also known as when it passes the horizontal line test, and every horizontal line crosses the graph exactly once. Let's decide briefly if the following functions are invertible, and we'll use a graph to do this. The basic graph of x squared is a parabola. You're pretty familiar with this shape, and you'll notice this definitely does not pass the horizontal line test. So the final idea here is it is not invertible. Again, because if you don't pass the horizontal line test, you can't find an inverse. And by the way, let me explain why. Let's say this value is y equals 4. Then there are two x values associated with it, -2 and 2. If I were to try to plug 4 into the inverse, I need to get one answer. And is that answer 2 or -2? It's not clear which. How about x squared when x is greater than or equal to 0? Well, if we only draw the x greater than or equal to 0 side of the parabola, sure, it will pass the horizontal line test. So you could draw little horizontal lines, and all of them pass through exactly 1. So I'm going to say invertible. And we should put reasons for these. So this is going to say passes horizontal line test. And just to give an answer for A as well, it fails the horizontal line test. Now let's look at x cubed. The graph of x cubed does not have that same parabola shape. It actually comes up on the right and down on the left. And sure enough, it will definitely pass. The question that you might wonder is right around the 0. It actually does sort of flatten out at 0, but only for one point. It never actually has 2 points that it'll pass through, so this one is again invertible because it passes the horizontal line test. So as long as you have this property of passing the horizontal line test, or the one-to-one property in general, you can say that an inverse exists. The final thought that I wanted to bring out is to point out that the log and the exponential functions with the same base, we had properties where they would cancel each other out. So what I would like to point out is that if I look at this as f of x is a to the x, and g of x is the log base a of x, if I compose these things, f of g of x would be a to the log base a of x, and the property right above would say these cancel and leave x. But g of f of x, if I do it that way, I would have g as the outside function, log base a, of a to the x, and again, based on your properties, these cancel and leave x. Remember, if you can compose the two functions in both orders and just get x, they are inverses. So this was a property that we've been sort of talking about the whole time. Exponential and logarithmic functions with the same base are inverse functions.